Hi everybody, so my name is Kaarel Hanson. I am leading space activities at Guardtime. So we are a cybersecurity company from Estonia. And I'm going into more, maybe slightly technical side of things today here. And we'll talk about blockchains in general in the cybersecurity domain, but also I will dive into a bit into a couple of solutions in the space domain. So, of course, a legal disclaimer. So Guardtime is a deep tech company specialized in building cybersecurity and complex data management solutions, mainly leveraging blockchain and distributed ledger technologies. So our company was founded in 2007 with the aim to make the world's information universally reliable. We've been involved in the space domain since 2018, and our main domain experience is in the Earth observation, and also lately we've moved into the space surveillance tracking and space traffic management area as well. And as always, in the solutions that we implement, we utilize mainly our own core technologies. And when we talk about cybersecurity, cybersecurity has many shapes and forms. So the area that we are focusing on is in the data security, data security side. So we need to maybe understand what are the sides to this data security. So CIA triad doesn't have anything to do with the intelligence agency, but it states or it refers to confidentiality, integrity, and availability sides of this overall information security model. So confidentiality, I think, is most common one, which is usually the area which is referred to as cybersecurity. So it's the idea is that we want to prevent the disclosure of information to unauthorized individuals or systems. The second one, if we go to the left side, is availability. But the availability doesn't always look like it's cybersecurity related. However, in fact, well, making sure that information systems are available and accessible is an area of the security model. And the last one is the integrity, which is about maintaining and assuring the accuracy and consistency of systems and data. And the part that we are mostly involved in is this integrity side. Now, when we dive into the technology side, then these two terms that we have on the screen right now, so blockchain and DLT meaning distributed ledger technologies, is somewhat, well, people think these are synonymous. However, in fact, they are different, or one is part of the other, to be more precise. So to clarify the situation a bit, then blockchain is in fact just a data structure for storing information in a chain of blocks. So the name comes from because it's a linked chain of blocks. This is essentially a database, just a means of storing of information, and it doesn't say anything about how the entire system or solution, which is solution is in fact, let's say, designed or deployed. So, but when we talk about distributed ledger technology, then DLT, in fact, is a digital system for recording transactions and data across multiple locations or nodes simultaneously, ensuring these very important properties. So it's transparent, secure meaning the information that is submitted into a ledger. So a ledger is a record of events. These events cannot be removed from the record, only read and appended. And then there's also the decentralization part without central authority. So this was the key idea behind the distributed ledger technologies. So to remove a central authority from the middle and provide or give community the authority over the activities and information that is stored in the so-called network. So this is representative of a very simplified distributed ledger technology-based network. Every node is connected with each other, and then also there is a term there called consensus, which means that every node or let's say majority of the nodes or the parties in the network need to agree that this information that is to be submitted or stored in their ledger is in fact correct and authentic one. So they have to come into agreement. So this is called consensus. And this is, let's say, a common approach how cryptocurrencies are designed and used today. So how, and now moving on to Guardtime's approach. So we have taken the same idea. So idea of a blockchain, but we have slightly changed the approach how we actually use the blockchain. So blockchain is a database. For example, in the most common case in cryptocurrencies, the transactions performed in this network are then stored on the blockchain and visible to everyone in the world. Now, we do things a bit differently. So we have the blockchain, which is a database, but we take a piece of information, so it can be any digital data, it can be a document, a log line, it can be even a virtual machine image. We take a hash of this, so a hashing function is a one-way function that creates essentially a fingerprint of a piece of information, and then we store this hash on the blockchain. So this means, in fact, that we sort of like anchor this piece of information into the blockchain. And in return, what the blockchain returns is a proof of registration. So this essentially is a timestamp that includes relevant and necessary information to prove that this piece of information was, at the time of storing, or let's say, the data itself has remained the same as it was when this proof of registration was created. Or it proves that the information has changed, for example. So this is how we have made the blockchain solution work for us. So this is our proprietary blockchain solution called KSI. We host it, we run it, we maintain it. It's a proprietary one, but we provide the timestamping as a service. Well, the blockchain as a service, timestamping information. And this is a core technology that we use to implement different kinds of applications. So it's a very, let's say, hidden away technology, because we don't want to, or blockchain itself is not value. Blockchain is a tool to provide value for certain use cases and to resolve certain problems. And what this timestamp then, let's say, proves or provides is that the asset integrity, so that the data has not been changed since signing. I need to make a slight clarification here that the signature is not a digital signature. So if you use this word in Estonia, then a signature refers to a digital signature. But no, this, because we coined this term years and years ago, so we didn't know that it would become such a good thing, to be honest. Then we have stuck to this terminology, but it's in fact not a digital signature that we create. I will slightly go into this more as well. Also, we prove the signing time, because the time of the signing of this information, or time of creating the timestamp, is very relevant, because it must be possible to prove that certain information was as it was at that time, specific time. And then what also we can prove is signing entity, but this is just the entity, some person, machine, that's information, meta information that is stored inside the timestamp itself. And now I will provide a couple of use cases, blockchain use cases that we have implemented, some more generic ones and some more specific to space area. So I will go into more details with those. So very simplified one is long-term data integrity of data archiving. So when we archive information, we want to make sure years and years in the future, that the information that was archived was in fact has not been altered during time. So this is a very simplified use case which we have implemented as well. Audit trail authentication. So audit trails are very important, or audit trail is a very important tool in the world of finance, for example. So because a lot of, let's say, money is at stake there, all activities, transactions, and so on must be logged. A lot of information is created, and if somebody would come and say or claim that certain money from my bank account is lost, basically. So what the bank can then do is they can, let's say, secure themselves by anchoring every piece of information that they have ever logged to the blockchain, and then go into court with this information and say that, now see, these are the log lines that we have captured in our system that represent activities related to your account, and these say that now you have transferred this money to that account, and then there is no case anymore. So this is quite relevant use case in finance, in the world of finance. Also, what can be done with blockchain is asset management and attestation. So tokenization today is a big thing. We can tokenize basically everything, physical things, digital objects. A solution that we created in this specific domain is that let's imagine there is a very large construction site where there is a very large number of different vehicles entering the construction site. So these vehicles can create a lot of problems, even fatalities, within these large construction sites. And therefore, these vehicles need to be attested or inspected prior to allowing them into the construction area, for example. During the inspection, let's say the physical object is tokenized, it's stored in the blockchain, and then when the driver takes the car or the lorry goes into the construction site, the guard at the gate basically scans their provided QR code, and then they are provided the information that yes, this car can enter the construction site, and the inspection information is correct. The car is the registration number is the right one, and so everything is good. And in this way, illegal entries can be blocked, basically. Then we have this, what we call a decentralized identity management. So this is very closely related to, and in fact, it's quite synonymous with self-sovereign identity. So, for example, if you go to a supermarket and you would like to purchase something that is age restricted, then the cashier would need to know that if you are eligible to purchase this good, for example. And what you do is you provide your identification card. Now, in fact, what you do is you reveal information that is not relevant to the cashier. So the cashier only needs to verify that you are of certain age. They don't need to know your name. They don't need to know your nationality. They don't need to know any other information that is actually written on the piece of plastic. So what this decentralized identity management, in fact, supports is that if you go to the supermarket, you have a digital wallet in a phone, for example. You go to the cashier, and the cashier says that, okay, please prove your age. So you only prove the credentials or the information through your digital wallet to the cashier that is only relevant for this specific use case. So we provide information that, yes, I am more than 18 years old, for example. So this is a use case for that can be solved by blockchain or distributed ledger technologies. Now, going into more slightly space-related, but again, space-related things is supply chain traceability. So supply chains have been talked about quite a lot during the past couple of days. Supply chains are susceptible to different kinds of attacks. And why I've stated food here is because we have implemented the solution in the food supply chain domain, which I will go into more details. So supply chains are very good use case for blockchains or distributed ledger technologies. Then attribution of origin and chain of custody. So this again is slightly related to supply chain, but it's more related to digital supply chains. And this is more, well, I will again talk in more details regarding this use case based on a solution that we have implemented in the Earth observation domain. And finally, we have this end-to-end communication channel security, which is about securing the information sharing and information distribution between different parties in a network. So again, I will go into more details with these three use cases. So regarding supply chain traceability, so what we start with is the blockchain, our core technology. And so what we have done in that area is that we have implemented this supply chain traceability solution, which has different parties in the system. So in this specific case, in the food supply chain traceability, the aim is to prove that the crops that the farmer, for example, grows is turned into certain food and then ends up in a supermarket is the authentic food, any kind of authentic food, let's say, and the consumer can verify that this food, in fact, is what it states on the bottle as it is, for example. So let's go through a simple use case. Is that so? There is a certain region in Spain, for example, where there is certain type of olives grown that is turned into olive oil. So the farmer needs and wants to make sure and prove to the end consumer that in fact the olives come from this specific area. Now, how we make sure that these come from a specific area is not, let's say, directly related to the blockchain-based solution, but what we have implemented on top of this, which is in fact not visible from this diagram, is that we use Galileo technology called OSNMA to authenticate the positioning of the information capturing point, basically. So this is quite a novel technology. So basically, a flag or certain information is stored in the navigation signal, which is transmitted to the ground, and then the transmitter, the smartphone, then basically could verify that the signal that is transmitted from Galileo satellite to the ground is in fact originating from the authentic source. Authentic source being a Galileo satellite, not some other piece of hardware that is transmitting information nearby. So this is a very common way to overcome spoofing attacks, for example. So farmer does something, so basically captures information, captures pictures and so on and so forth. Information is anchored to the blockchain, information is sent to the central system. The central system name is called S4G because it's synonymous, or it's short for Space for Green. It's a project that we are currently working on. And all information through the entire supply chain goes through the platform. All information is anchored to the blockchain, and then the final end consumer, let's say, goes to the shop, takes the bottle of olive oil, scans the QR code that's printed on top of this, and then receives the full end-to-end list of activities and events that have been created or, let's say, captured in the process of creating this end product. So, traceability, visibility. Now, moving on to the next use case regarding attribution of origin and chain of custody of AO data. So let's say that I have just purchased an image from an Earth observation service provider or data supplier because I need to process this image and provide certain information to some customer that I have, for example. Now, I have received this picture, I have processed the image, and then I get information, or the outcome of this processing is not what is expected, for example, for some reason. And then I discovered that, the picture I was looking at actually looks like this, because I had it the other way around. Okay, now, I know that bunnies and Easter are synonymous, basically, but I don't think Easter Island looks like this. So I turn to my data supplier and I tell him that, okay, so I received this image. I don't get the expected outcome from the processing. Could you please tell me if this is the image that you indeed sent me? And the data supplier comes back to me and says, no, this is not the image I sent you. I sent you this image. So this is the correct one. So this indeed is Easter Island. So who has the right here? So where did I actually get that image, the falsified image? So we had this discussion yesterday regarding AI. AI has very good benefits in this domain specifically, because if we have large and large amounts of information, processing this using data mining and AI techniques is very beneficial, but also AI can create a lot of problems. So this being one of them. A couple of more examples for you. So this seems like, this is some city. I don't know where it is. Not very good picture, but an Earth observation picture. Now another one, bad quality, but still seems like a city. And here we have quite a good image. This is a quite good resolution image of some city. I don't, again, know. We have parks, Central Square, and so on. But now the problem is that none of these exist. So these are all AI created. And this is a big problem today, because we don't know where this information comes from, because AI has become very powerful. And AI attacks in the area of Earth observation and also in the geotechnologies is basically rising. So how to overcome this problem? So we have implemented this solution where once information on the Earth observation images are captured on ground in the ground station, we take this event and we anchor this event to our blockchain. When there are certain activities done on this information, so we have this L0 image, we anchor this into the blockchain, then we do some certain processing, we have the L1 image, anchor this activity and the new information onto the blockchain. We perform further processing, we do dissemination and so on, and then we end up with this L2 product. Everything in between has been anchored to the blockchain. And what we have in between those circles are links of chain. So what we do is we link each activity performed into a single chain, creating what we call a provenance chain. And this allows the end user to verify that this product is authentic, and they can check from which source or image this specific product was created from. So it has been created from the last one, from this one. So there is a cryptographic link, cryptographic proofs in between stating or saying that this final product in fact is authentic and correct. There is one, let's say, missing link today in the whole EO data supply chain, or the supply flow, let's say. So there are so-called two different chains. So the first one is when the image is captured on the satellite, stored on board basically, and then transmitted to the ground. So let's say this is the first chain. And then the second chain is starting from the core ground station, and from then on we have, let's say, visibility of the information. We have tagged or anchored the information to the blockchain as close as possible to the source, but still we are missing this first part. So we are looking into that area today as well, but as the technology that we have today requires access to internet, it's a bit difficult to perform this today, and the capabilities of the satellites are not there yet as well today. However, we intend to get there. So as we can see, the raw information is not, let's say, time-stamped, not stamped yet. So, moving on to the next use case is end-to-end secure communication and data sharing in Cream. So CREAM is a cornerstone activity that the European Space Agency has initiated through their space safety program. So CREAM in short means collision risk estimation and automated mitigation. The idea behind CREAM is to increase the safety of space assets, to be more precise, by providing this platform where satellite operators can easily verify the risk if there is a conjunction, verify the risk if there is a risk or if there is not a risk, and they can negotiate in case of potential collision with the other operator, so which party would have to perform a maneuver. So how it works today is that the operator receives an alert from a catalog, space catalog. So they need to do something with this alert, because alerts they can be disastrous, but majority of the alerts in fact are saying that there is a small chance that your satellite is colliding with another satellite, but this risk needs to be evaluated first. So the operator turns to some service provider and asks, okay, so could you please perform more specific observation of my satellite to determine if the risk of collision is in fact there. So the service provider, or the collision avoidance service provider, or conjunction analysis service provider, performs these observations and then comes back, says that no, your risk is very small. In fact, yeah, the two satellites are passing by each other, let's say, in the distance of 500 meters. So it's just a scare. Now, if the service provider says that yes, there is a very certain potential that this conjunction, in fact, will end up as a collision, then the satellite operator needs to know, okay, now needs to find out who is the other operator. More than often, the satellite operator might not even know what the other satellite is, but if you know who the satellite is, you might not know who the satellite operator is, because there are loads and loads of operators around the world. You find out who the operator is, you still don't know, okay, how can I get in contact with them? So this has been a serious issue before, because there have been a couple of very close approaches, because the operators were unable to get in contact with each other because they didn't know who the other party is. So the idea in CREAM then is to create, again, this coordination system. This is not the entire coordination system, but this is just the part that we have implemented there. A coordination system where, well, it's not just the coordination system, it's more like an ecosystem which brings together the operators and also the service providers. Eventually, it would be very nice if satellite catalog providers would be there as well, but today we don't see this happening. But so how our technology is used there is that we use our technology to anchor the information that the operator needs to exchange with the coordination platform to the blockchain in order to verify and make sure that information indeed that is used to perform certain operations and calculations is authentic one. Because if, for example, this risk evaluation or risk assessment is performed on information that is in fact, let's say, tampered, then the consequences can be very severe, as we can imagine. So it's a very similar approach that you saw on the picture before regarding the supply chain traceability, but the use case is slightly different. But still, so the information is anchored to the blockchain. The information together with the timestamp is placed into an envelope sent into the coordination platform, and on the coordination platform we can verify and check that this piece of information that was received in fact is the authentic one. And also we register that this information has been received from this specific user for any kind of disputes later on. So this is the core approach, how the end-to-end security of this data sharing is performed. And one might ask now that why don't we actually use the blockchain itself to share the information across all these users? Yes, this could be done, but the problem here is that if we think about what are the core principles of a distributed ledger technology is that the database is synchronized between every node in the network. Now, the operators might be very interested in having all this information in their system as well. However, let's say the service providers might not be very interested in hosting gigabytes and maybe terabytes of information in the information system because they don't really care about that. So that is a problem. So this is actually a revelation or a finding that we received when we first started with experimenting blockchain technology in the area of SST or satellite and service, satellite surveillance and tracking domain. And we discovered quickly that the conventional use of a blockchain in such a scenario is not very, let's say, useful, because due to the properties of blockchain technology. Yes. Okay, and this actually concludes my presentation. So thank you for listening, and I hope you learned something here today.
Kaarel, I was listening to your presentation and I was thinking, do you already have a good slogan to selling your cream service?
No.
Let me provide you with one. It's just for free.
Very
Cream, the crème de la crème of secure connections. How does that sound?
Maybe indeed.
Maybe.
Maybe
Well,
indeed.
I can come up with a few more. Ladies and gentlemen, do you have any questions for Kaarel? Nope. Oh, there's a few. Do we also have a microphone for those questions so they are well preserved in our recording? So please raise your hand again. So there's a question over there. Go ahead.
Usually in blockchain, you actually have data that is public to all the participants of the blockchain. How can you actually make sure that the data is encrypted enough that it is not like, how can you secure the data in the blockchain technologies?
So the idea of a blockchain is transparency, or distributed ledger technology in general. So we never encrypt information that is stored in the blockchain. Well, yeah, it could be done. So you could encrypt information, place encrypted information in a public database for sharing between, or for sharing with some other party in the network, for example. But that is not really the use case for a blockchain. Then you could just, let's say, encrypt information and send directly to your recipient, for example. So data encryption is not what blockchain is really about. It's about synchronizing information across different places and data immutability, meaning that no information that has ever been stored on the blockchain cannot be removed and cannot be tampered with because of the architecture of a blockchain. So once a block is added into the chain, a reference from the succeeding block, a reference of the preceding block is added into the new block, meaning that it's a hash function-based activity that is performed there. So if some information in the past, so to speak, is tampered with in the blockchain, then everything that is stored in the future or has been stored cannot be verified as true anymore.
Super easy, isn't it?
Yes.
Right. Now, we had one more question. Go ahead, mic is on your way.
Thank you. So the application of Earth observation data and tracking the validity of that, do you see any satellites who already can give the signature or a hash together with the raw data? And the other thing, the next application, like these tracking of space assets, have you seen any these radar tracking stations? Can some of them give a hash together with their tracking data so that later you can identify correctly, like put it into a blockchain and see that if all that is correct. I understand that this is like the first link in the chain. Like if the correct data is coming from the satellite, then you would like to put a signature already on the satellite, and then the other application of the tracking of the assets.
Yeah, that would be the, let's say, the ideal solution, ideal approach. So stamping or tagging the information as close as possible to the source means that there is virtually no possibility to tamper with the information, or at least it can be verified that this information has not been tampered in any way. So to answer your question, no, we haven't done this as close to the source yet. Certainly we would like to, because this would provide more value for the overall solution. So if we could already stamp information coming from or captured in the radar station, that would be so-called holy grail, let's say. So no, we haven't got that close to it yet. So as I mentioned regarding the Earth observation images before, is that we haven't yet come up with good enough technology that could be used already on the spacecraft because of the limitations of connectivity.
So we'll take one last question. There's one in Menti. The system assumes that operators are involved in the system. If the operator is unknown and not involved, you still have the same problem that you are trying to solve.
Yes, partly at least, yes.
And partly at least, no.
Partly yes, partly no. Indeed, it can, the overall, let's say, CRIM platform can still perform certain activities, certain analysis, certain negotiation. Let's say one side of this. So true that you wouldn't know who the other operator is, but still it provides the value of what I just mentioned before. So yeah, it is still would be a kind of a problem.
Right. I'm afraid we've run out of time. Thank you so much, Kaarel, for a very detailed, technical, and mind-blowing presentation. Those of you who have more questions for Kaarel, I'm sure you'll find him in the audience. We have a pause coming up soon, so give him a round of applause.
Thank you.